We are live to tape, so once again, good morning to you all this May 10th, and welcome to our Monday plenary. This is our last lecture in which I'll be introducing new material. We will, by the end of this morning's lecture, have covered what is in the syllabus, namely the remaining topic, Newcomb's problem, a very special kind of prisoner's dilemma, as you'll see, and I think an interesting one. It's also kind of a game that we're all going to play together in class, and we'll discover what the result will be. But the final class of the semester officially, according to the academic calendar, is the 17th. That's next Monday. So as some of you are mindful already, and I'll repeat this for your benefit, we do have class next week, but I will not cover any new material. Instead, I will throw the session open for any questions that you may wish to raise. In the first instance, questions about what we have and will have covered during this third section of the course, namely Zeno's paradoxes, Anselm's ontological argument, the prisoner's dilemma, both the two-person case and the n-person case, and also today Newcomb's problem and its applications that I'll look at on Thursday in our breakout group with Section M. But next Monday, I'm amenable to discussing any questions that you may wish to raise based on those readings, or indeed to broaden our discussion and look at philosophical questions that we haven't tackled this term at all, but may have occurred to you in the process of going through this course, or indeed to broaden the discussion to larger issues that pertain to our everyday lives, particularly in this pandemic situation. So I'll be very happy to discuss philosophically with you anything you want to raise next week, including things that are beyond the extent of this curriculum. But as you probably appreciate by now, there's really nothing beyond the extent of philosophy. That is, we can philosophize about anything under the sun. So I'll be happy to, review things that we've covered, or to broach new subjects with you in our final lecture next Monday, okay? And that will wrap up the course officially. So, without further ado, let me just now ask whether any of you have questions about what we covered last week, namely the prisoner's dilemma, before we launch into Newcomb's problem. Do you have any questions about the prisoner's dilemma itself? Either the two-person case or the iterated case or the n-person case, or why it's a dilemma, or tragedy of the commons, or free riding, or any of the other topics that arise. Any questions at all? Either enter them in the chat room or unmute yourself and feel free to speak. So far, I infer that you're all happy with the prisoner's dilemma, that you all have a pretty good handle on what it is and why it's a dilemma. Let me ask you, are you now better aware, perhaps, of just how broadly applicable it can be to many different kinds of situations, especially the n-person case? Has this become clearer to you from last week's treatment? Yes? Okay, good. All right, I mean good and not good, because as you can see, especially with the tragedy of the commons, it unfortunately is a model that explains all too well why we have done such irreversible damage to the environment and to particular habitats and so forth. If everybody defects in their own self-interest, then it produces a collective detriment, basically, and that's the nature of the dilemma. Okay, so you understand that. But it's not always irreversible. If people start cooperating, then, of course, we can change things and undo and reverse some of the damage. We can't bring back extinct species unless we get a hold of their DNA and figure out how to clone them from scratch, which no one can yet do. But in any case, the main thing for rational philosophy is to figure out how to encourage more people to cooperate in these situations and fewer people to defect. Okay, that's last week's material. So if you're ready, then we will tackle this very interesting variation on a prisoner's dilemma. It is a prisoner's dilemma in its structure, but it's a very different kind of a game in the actual play, because you're not playing against another prisoner, nor are you playing against a group. You're playing against a very wealthy and very potentially generous demon who wants to give away a lot of money. And the name of the game is for you to win as much as you can. So we'll get to Newcomb's problem in a moment. I just want to say that there are many, many other paradoxes and puzzles, of course, in philosophy, and also which impinge on economics and psychology and political science and artificial intelligence and so forth. As you can see, these cognitive puzzles that humans are smart enough to invent, but not always smart enough to solve, do have traction in other disciplines. So I would just mention to you, before we launch ourselves into Newcomb's problem, that there are other kinds of paradoxes that have also given rise to some interesting science fiction, and that would be the class of paradoxes known as time travel paradoxes. Maybe you've already encountered some of these things in movies, or I don't know if anybody reads short stories anymore, but a lot of good science fiction used to be written in short story form as well as novel form. But the basic premise of the time travel problem, or the time travel paradox, is as follows, and I'm just mentioning this for the sake of culture. It's not required, but it might interest you, especially if you haven't encountered it before, that there's nothing apparently in physics that forbids time travel. I mean, there are no explicit laws that I'm aware of that say we can't travel back in time. No one's invented a time machine yet. But such things are not in any sense defying the laws of physics such as we understand them, just as it's possible in principle, for particles to travel faster than the speed of light, in which case they would turn out to have negative energy, which is something we don't encounter in our everyday world. But the universe is always a stranger place than we deem it to be. And as you know, as science goes on to discover all kinds of things about space and galaxies that we never knew, quasars and black holes and white holes and wormholes and all kinds of things going on out there, which prove to be stranger than fiction at times. So the more we learn about the universe, the more we discover that it's not what meets the eye. Again, reality is a very different thing from appearance. But here's the point. The paradox arises as follows. If you were, let's say, to invent a time machine, and I hope one of you does, and if you do, I volunteer to take a ride on it one time, okay? But anyway, if you invent a time machine and you go back in time, suppose then you did something accidentally, which through a long chain of causal events prevented your parents from ever meeting. I mean, you might have just kicked a stone, right? Or you might have uprooted a plant, or you might have killed some animal, but you might have done something to interfere causally with the past. And through a long chain of cause and effect, that thing that you did to change the past might, for the sake of argument, have to, it's not the same as the butterfly effect, Alexandra, that's something else. Or at least you can think of it in those terms, but that's chaos theory, that's a different thing. But if you went back and changed some event in the past that has a causal effect on the future, for all you know, you might have actually prevented your parents from meeting, in which case the question is, how could you ever have been born? And if you were never born, then of course you could not have invented a time machine and traveled back in the past. So that's a paradox, because if we travel back in the past, if we're able, on the condition that we're able to interact causally with people and with things and with events, then we could presumably go back in the past and change the future. But that means everything you learned about history could be wrong. right? I mean, you could have studied history, then go back in the past, and through some actions that you take in the past, change the course of history, and therefore, in some sense, obviate or negate or falsify everything you had already learned. So how could that happen? That's certainly paradoxical, and no one really has an answer to that, but those are the kinds of problems that arise when we start allowing time travel. So that's one kind of class of problems, time travel problems that you'll encounter in science fiction. The butterfly effect, Alexandra, as I understand it, has to do with chaos theory. It's the idea that a butterfly, chaos theory in general is a different topic, and it's not paradoxical at all. It's rather, unfortunately, in some ways, very, very rational and empirically verifiable. Chaos theory simply informs us, without the mathematics, we don't need the mathematics to understand the concept, that in some processes, in many processes, a very small change of initial conditions in the process at the beginning or near the beginning can result in a very large change in the effects at the end. All right? So that's basically small difference at the beginning can lead to a very large divergence, very large difference of outcomes at the end. And that is, in essence, what chaos tells us. It's all determined. It's not random. But I'll give you an illustration in a moment. The butterfly effect, such as I'm familiar with it, maybe you've read about it in a different context, but the typical butterfly effect refers to the fact that a butterfly flapping its wings somewhere in the Caribbean could actually give rise to a hurricane eventually through a very small perturbance. Could be amplified through a series of naturally occurring events and could therefore contribute to the formation of a Category 5 hurricane. And that's a kind of hyperbolic illustration. We don't really ever expect a butterfly to cause a hurricane, but that's what it's become known as. Okay, Alexandra and others, the butterfly effect is to tell you that the moral of the story, it's not literal. It's not the butterflies cause hurricanes, but it's that a small thing at the beginning can lead to a large thing down the road. And I think a more apt illustration of that principle is the following. Imagine that you take yourself to the summit of a very tall mountain, which you can ski down. Suppose it's snow-covered and you can ski down in any direction. So you're standing at the summit of the mountain, and you're taken up by helicopter, and you ski down, okay? And you come to the base of the mountain, and that was fun, and you arrange to get taken back up to the top so you can make another run. Now, let's say the second time that you ski down, you turn your skis a little bit. So the angle between the first run and the second run is very tiny, right? You just point your skis slightly to the left or slightly to the right of where they were last time. Very, very small angle. And then you ski down the mountain again. Depending on the height of the mountain, you could end up very far from where you were last time at the bottom. You get this? Right? You could end up miles away from where you were. And that's a better, I think, a more literal and plausible illustration of chaos theory, because you can try the experiment. So a small difference at the top of the mountain, in your path of departure, your angle from, differing from where you skied down the first time, could lead to a huge divergence at the bottom of the mountain in terms of where you end up compared to the first run, and so forth. Or toss some corks in the ocean. Don't do this because we have enough junk in the ocean, but imagine some corks tossed in the ocean, and they are initially very close together, but different conditions acting on them will serve over time to disperse them. This actually happened with a load of rubber ducks. I don't know if you've ever seen this video, but container ships lose containers all the time in rough weather, and we have so much container shipping going on. And one time, It's funny, it's also not funny, but the amusing part of it is that a container went overboard and smashed open, and it had, among other things, a huge load of rubber ducks. You know, these rubber ducks that people supposedly play with in the bathtub. I mean, I don't own one, but I know that they sell them. So this load of rubber ducks was dumped into the ocean, and since the crate opened up and spilled them into the ocean, they were all very close together initially, right? But because of wind and waves and small differences in their initial conditions, they ended up dispersed all over the planet. They washed up in, I think they washed up in Norwegian fjords. Some of them washed up on beaches, you know, in the southern hemisphere. They got separated over a period of years and stayed afloat and were carried by wind and waves and other effects and ended up dispersed all over the planet. That's the butterfly effect, okay? So a small difference at the beginning leads to a large difference at the end, and that's part of chaos theory. Is that clear? But that's not a paradox. That's perfectly understandable. Whereas going back in time and accidentally killing somebody, let's say you accidentally doing something that disturbs a chain of historical events such that it prevents you from ever having been born, is genuinely paradoxical, because if you went back and interfered with your own eventual birth, how could you go back? You wouldn't be there to invent the time machine and go back. So that's what's genuinely paradoxical, okay? So yeah, good. I see that, you get that. And it's a different problem if we're looking at time travel. But there are many, many kinds of paradoxes that involve time travel, not particularly chaos theory. Okay? So the thing we're going to look at this morning is not a time travel problem, and it's not a paradox, it's a dilemma. Newcomb's problem was first published by a great philosopher, a late great philosopher at Harvard named Robert Nozick. He died a few years ago. And it was published in 1969 in a book of essays, collected essays dedicated to an important philosopher of science of the 20th century, namely Carl Hempel. But this problem surfaced in that collection of essays, and Nozick learned about it, and I think he was the first one to learn about it, and he wrote it up. So in any case, it went viral, although in those, at the time, in 1969, we didn't have that expression except for viruses, because we didn't have computers. We didn't have PCs, we didn't have the internet in 1969, but it was still possible for something in print to take off in popularity and become very widely read and very widely discussed. So that was the equivalent back in those days of going viral. So everybody found out about the problem, and it's been discussed ever since. And that's why we're going to look at it now. And it belongs to this class of problems called predictor problems. And it's when you have to make up your mind about something, and when you have this being who's going to predict what you're going to do, and then you have to make a choice based on what you think the being predicted, or based on the accuracy with which you estimate the being's prediction, and depending on how much you credit or believe the being's ability to predict, you'll make a certain choice. If you disbelieve the being's ability to predict, or if you are tempted by dominance theories, we'll see, you'll make a different choice. And there's no resolution to this because it's a dilemma, but there are going to be very good reasons for choosing either horn of the dilemma to impale yourself on. It is technically, according to the structure of the problem, a prisoner's dilemma. It has the exact same structure. So you'll immediately recognize, those of you who are familiar with or who have now assimilated the conflict between dominance reasoning and maximizing expected utilities, will recognize this immediately when we look at the Newcomb problem. So we're going to have that conflict of principles. But what you stand to gain in this case, there's no downside. You're going to win either way. It's really a question of whether you're going to win $1 million or whether you're going to win $1,000. Okay, that's the big decision you have to make, and you risk on the one hand winning $1 million or getting nothing if you're wrong, and you can always get 1,000. But you may not get the $1 million, depending on, again, the choice you make and what you think the demon is predicting about your behavior. So it's a predictor problem, and it leads us into this very interesting kind of territory. And then I'm going to explain it to you. I'm going to show you the diagrams and go through the reasoning and explain the mechanics. There's a certain sequence in this game which you have to respect. And once you all get it, I'm going to ask you to make your own choice. Suppose it's your turn now to play against Newcomb's demon, and Newcomb's demon has no interest in anything except making right predictions. Newcomb's demon is the sort of creature that has infinite money. He has even more money than Jeff Bezos, and he's happy to give it away. He's equally happy not to give it away. That's not his interest. He'll give it away to you if he predicts correctly what you're going to do, depending on what you do, and or he'll give you nothing, depending on, again, the prediction he makes and your behavior subsequent to that. But he's not interested in money. He's only interested in correct predictions. That's what the demon lives for, is to make a correct prediction about what each player is going to do. And the demon has this uncanny ability to do it with a high degree of perfection, very close to 100% of the time the demon is right. And you can watch. You're allowed in this game to watch lots of players play before it comes your turn. You're standing on line with a number, and when your number comes up, you play. You get only one turn. And you get to see, if you're tracking the results, that the demon's almost always right. But then it comes your turn. Okay, so let's look at it and see how the game works. And we'll make sure you understand what's going on, and then after that, we'll play the game. Okay? So let me just share the screen with you. Does everybody see Newcomb's problem? Are you all seeing it?
Yes.
Yes?
Yeah.
Okay, thank you very much. All right, good. So here's the deal. At first blush, it doesn't look like a prisoner's dilemma. It's a game, but you're going to see the matrix representation will be exactly the structure of a prisoner's dilemma. But it's called Newcomb's problem, and apparently it was invented by a physicist named, I think, Newcomb. So it got his name in the literature, but it is Robert Nozick, the Harvard philosopher, who actually published it originally along with his analysis. And he tried it on many students at Harvard in his philosophy classes, and I'm not going to tell you their results, but I'm going to wait and see the result of this class. Okay, so he understood the problem very well. Now here's the sequence of events. First thing that happens is when it's your turn, each of you one at a time will play against the demon. And the first thing the demon's going to do, he's not a bad demon, he's just a rich demon who wants to predict your behavior. So the demon will predict your choice first, without talking to you. The demon in its own mind is going to read your mind and predict. Now you only have two choices. You can choose box B alone. When it comes your turn to play, you will choose box B, or you will choose both boxes, okay? Those are your choices, box B only, or indeed both boxes. And by that I mean you'll get the contents, okay? If you choose box B alone, you'll get whatever is in box B, but you can't see into box B, it's gift wrapped, okay? If you choose both boxes, you're guaranteed to get the $1,000, that's $1,000. That's sitting there in box A, it's transparent. You could see the 1,000 sitting there, but you don't know what's in box B. And box B is going to contain either $1 million or nothing, depending on what the demon predicts about your choice. Okay? So first the demon makes its prediction. Are you going to choose box B only? Or are you going to choose both boxes? Those are the only possible alternatives. If the demon predicts at the next step If the demon predicts that you will choose box B only, it puts $1 million in box B. If the demon predicts that you will choose both boxes, it puts nothing in box B. So that's what happens first. You step up to play, the demon reads your mind, it predicts whether you're going to choose box B only, in which case it puts $1 million in there, or if it predicts you're going to choose both boxes, doesn't put anything in box B. The 1,000 is sitting there the whole time. You've already seen it. It's yours if you take both boxes. You can't choose box A alone, though. You have to choose either box B alone or both boxes, right? And then once the demon has made its prediction and made its move based on its prediction, then it's your turn to choose. And you're either going to choose box B only or you're going to choose both boxes. Is that clear? That's how the game is played. Okay? If you choose box B only, you get to open box B and see what's inside. If it's $1 million, you keep it. If it's nothing, you keep nothing. You get nothing. If you choose both boxes, you still get to open box B. But if the demon correctly predicted that you're going to choose both boxes, it puts nothing in there. So you get the 1,000 no matter what. But if the demon incorrectly predicted that you would choose box B only and you choose both boxes, then you actually get $1 million and 1,000. Okay? But the chances of that are very, very small. So does everybody first understand that the sequence before we look at the actual analysis? Are you clear about how the game is played? Or do you have any questions about this? This is, very important that this sequence be observed properly. Are we clear about that? And the demon has an endless money supply. Again, the demon doesn't care if it has to give away $1 million to every player. Doesn't matter. The demon has endless money. Is everyone clear? Yes? Okay. So far, so good. I'd always like to hear from a few more people. Okay, that's good. I'm getting some yeses. And that's fairly straightforward, but it is important that you observe the sequence of play and you understand how the sequence of play unfolds, and that you see this always. The 1,000 is sitting there. If you choose both boxes, you know you're going to get that. At least you never are able to see what's in box B until after you choose. Okay? And then obviously you're going to find out one way or the other. All right, if everyone is happy with the way the game is played, then we'll look at the analysis, and you'll see immediately that it's a prisoner's dilemma. Okay? So I've set it up in the usual matrix representation, and you are, in this case, sitting here as a player 2, right? The demon is player 1. So first the demon predicts what you're going to do. And if the demon predicts that you're going to choose box B only, then it places $1 million in box B. If the demon predicts that you're going to choose both boxes, then it puts nothing in box B. But again, you can't see what's in box B, so you don't know. Box B either contains $1 million or nothing, but you don't know until you make your choice what it contains, all right? Then it's very simple. You then are going to choose. And if you choose box B only, and the demon predicted that correctly, then you do get the $1 million. If you choose box B only, and the demon predicted that you would choose both boxes, then of course you get nothing. If on the other hand you choose both boxes, if the demon correctly predicted that, then it put nothing in box B, so you get only $1,000. And if you choose both boxes and the demon incorrectly predicted that you would choose box B only, hence it put $1 million in box B, you get the $1 million and the 1,000. Okay? So these two outcomes, which correspond to the Nash equilibrium and the Pareto optimal outcome in a prisoner's dilemma, are the outcomes that most frequently occur because the demon's rate of successful prediction is almost perfect. It's like 0.9999% right. You watch all these other players playing before you, before your turn, and you see that invariably the demon predicts almost perfectly in every case. 9 times out of 10, 99 times out of 100, 999 times out of 1,000, the demon is correct, okay, in its prediction of what the player will do. Okay, so that's the payoff matrix. And then you should very quickly see that it is exactly the payoff structure of Prisoner's Dilemma, because this is the temptation to take both boxes, right? It's the largest payoff. Yeah? R is the reward for believing that the demon will correctly predict your choice if you take box B only. It's less than this, but not that much less, right? And this is what happens to you if you decide, hey, at least I'm going to get 1,000. You know, if I take both boxes, I'm not going to take any chances. At least I know I'm going to get 1,000. That's minimum guaranteed to you, right? You can't lose if you do that. So that's a little bit like the Nash equilibrium, because it's not that great compared to 1,000,000, but it's still positive. And that's the so-called sucker's payoff. If you actually take box B only, believing the demon will correctly predict it, but you happen to be very unlucky and you're one of the very few cases where the demon incorrectly predicted, then you end up with the sucker's payoff of 0. But that's exactly the structure of the Prisoner's Dilemma. The only constraint or the only specific instance in this case in which it differs, not in its transitive ordering, that's definitely the Prisoner's Dilemma structure. But in this case, S is 0, which it doesn't need to be in a Prisoner's Dilemma. It could always be negative. As long as it's less than these things, it could be anything, right? It happens to be 0 in this case. And also in this case, T plus R, T plus R, right, is equal to P. Okay? This is just a very special case. Right? But basically, T is equal to R plus P. The temptation here to defect is equal to the sum of the 1,000,000 plus the 1,000. But essentially, the temptation to choose both boxes is equal to the sum total of both of those payoffs. Those are special conditions, but they do not alter the fact that this is a Prisoner's Dilemma. And because of this, because of structurally it's a Prisoner's Dilemma, you already know, those of you who are, and I hope that's everybody in the room, you're already on top of this dilemma, so you know exactly that dominance will in fact prescribe that you choose both boxes without even looking a step further, and you also probably have guessed correctly that maximizing expected utilities will prescribe that you choose box B only. And if you've already figured that out, good for you. You're definitely on top of the situation. But let's do the actual analysis and see. All right, let's just verify for ourselves that the same principles of choice that diverged in the Prisoner's Dilemma are once again going to diverge in Newcomb's problem, and exactly in the same way. Okay, they're going to tell us the same story, but in, this slightly special context. So first of all, let's look at you as the player, and dominance should very quickly convince you that no matter what the demon predicts, right? No matter what the demon predicts, yeah? You're better off taking both boxes, aren't you? Because 1,000,000 plus 1,000 is more than 1,000,000 every time, and 1,000 is more than 0 every time. So therefore, no matter what the demon predicts that you're going to do, you're obviously better off taking both boxes, aren't you? Because the result in either case, independent of the demon's prediction, is that if you take both boxes, you're either going to get 1,000,000 and 1,000, just in case the demon predicted that you would choose box B only, and that's more than 1,000,000. And your other possibility is, if you choose both boxes, you're going to get 1,000 at least, which is obviously better than nothing. Just in case the demon correctly predicted you choose both boxes, you get the 1,000. So you're still ahead. Okay? So because this is better than that, and this is better than that, it's strongly dominant. In every possible state of the game, choosing both boxes dominates choosing box B only. So therefore, the dominance principle says, obviously, you take both boxes. Is that clear to everyone? I'm not asking whether that convinces you. I'm just saying, is that line of reasoning clear to you? That's the dominance principle again. Please tell me if that is clear.
Yeah, that makes sense.
Yeah, sure. We saw it in the prisoner's dilemma, right? It's exactly the same line of reasoning. Remember, in the prisoner's dilemma, it went in a parallel course. It said no matter what the other prisoner chooses, you're better off defecting. Why? Because T is greater than R and P is greater than S. So this is the same line of reasoning with the same payoff structure to support it, okay? So that's on the one hand. And maybe some of you are already convinced you're going to take both boxes. But then again, if we maximize expected utilities, we get a very different prescription. We get the other prescription. And this is easier to see. In fact, if some of you are still struggling with the mechanics or with the algebra, then it's much easier, I think, in this case, to see why maximizing expected utilities would prescribe box B only. And here's the reasoning. Just follow this. You've already watched the demon play this game with lots and lots of players. Like, let's say you've got 1,000 people who've played already before it's your turn. Doesn't take long to play. You're standing on line. You got your ticket to play. You've watched 1,000 people play, and you've noticed that the demon was correct in its prediction, no matter what the player chose. The demon correctly predicted it 999 out of 1,000 times. So that means the demon's probability of successful prediction at that point would be 0.999, yeah? Very close to 1, yes? The demon is always going to have that high of a success rate. So what does that tell you? It tells you that the expected utility of choosing box B is what? Remember, it's a sum of the probability that you choose box B if the demon predicted you would, all right? And the times the value of that, which is 1,000,000, plus the probability that the demon predicted incorrectly, predicted you choosing both boxes when you chose B only. So what's the probability of the demon's correct prediction? It's almost 1. It's almost perfect. So therefore, the probability, if you choose box B only, the probability that the demon correctly predicted it is almost 1. So it's 0.99999 times 1,000,000, which is almost 1,000,000, right? And plus almost 0 times 0, right? 0.00001 times nothing, which is almost nothing. And therefore, the sum of those products is pretty close to $1,000,000, right? So that means the expected utility of choosing box B alone is very, very close to 1,000,000, okay? Very close to $1,000,000. We're measuring now dollars and not utiles. So what about the expected utility of choosing both boxes? Well, the same reasoning is going to tell you that if you choose both boxes, right, the demon will have predicted it with the same high degree of accuracy, very close to 1. So that means that the probability of this, if you choose both boxes, the probability that the demon predicted it and put nothing in box B is almost 1. And that means that the probability of this outcome is almost 1. So it's 0.999 times 1,000, right? Plus what? Plus the probability that the demon incorrectly predicted at times the value of this. Well, the probability in this case is almost 0, right? Because if you chose both boxes, the demon predicted box B only with a very, very tiny probability, since it's such a high success rate of prediction. And therefore, the probability of getting this is almost nothing. It's 0.0001 times this, which is almost nothing. So basically, the expected utility of choosing both boxes is going to be approximately $1,000 based on the frequency of correct predictions that you've observed. So if your expected utility of choosing box B only is almost 1,000,000, and your expected utility of choosing both boxes is only around 1,000, which is greater. Obviously, the 1,000,000 is much greater, and so your expected utility of choosing box B only, your expectation probabilistically getting 1 million is much, much, much greater than your expectation of getting this. And therefore, you would choose box B only. Okay? And that's why maximizing expected utilities, in fact, conflicts with dominance, just as it does in the prisoner's dilemma. Remember, if both prisoners think that the other one's going to cooperate with greater than 50% chance, then they should cooperate. That's what the calculus tells us. And in this case, in fact, you're going to get the same mathematical result, even though the demon's prediction rate is actually much, much higher than a half. You've watched it. It's almost perfect. But it will also turn out, if you do the math, that even if the demon's correct prediction frequency is just more than a half, anything more than a half, then the expected utility of choosing box B only will still be greater than the expected utility of choosing both boxes. So as long as the demon's not flipping a coin, if the demon's flipping a coin, you may as well go for both boxes. But if the demon's frequency of correct predictions is greater than a half, and we know from the conditions of the problem it's really much, much, much greater than a half, then maximizing expected utilities will prescribe that you choose box B only. And therefore you stand a really high chance of getting $1 million. Whereas if you choose both boxes, you stand a really high chance of getting only the 1,000 that you could see in box A the whole time. Okay? Whereas again, dominance tells you that you're better off choosing both no matter what, because this is obviously better than, $1 million plus 1,000 is better than $1 million, and 1,000 is better than nothing. So, that reasoning tells you, dominance tells you, doesn't matter what the demon predicts, you're better off with both boxes. So does everybody understand how we just applied the two principles of choice, once again, that we saw in the prisoner's dilemma? Does everybody see how they apply the same way to this problem with actually the same result, the divergent prescriptions? Is everyone okay with this, or do you have any questions? Randy's okay? Okay, please tell me. I want to hear from you. Everybody understand what's at stake? Rachel's okay with it? Everybody else all right? Or if you have a question, please ask. Are you all busy figuring out what you're going to do with the money now? Is that why you're not answering? You're already spending the money, or are you online spending the money? Don't do that. We can't play this game in class. It would be impossible for me to raise this kind of money to conduct the experiment. It would be unethical and probably illegal, so we can't really play the game, but we can pretend to play the game. So that's what we're going to do next. I'm going to ask you not to collude with each other. I'm going to ask each of you, of course, you're all wired on a different channel, so it should be easy. I don't know if any of you are sharing an internet connection this morning, but on the assumption that you're not, then I'm going to ask each of you very, very quietly, on your own time, if you understand the game, then I'm going to ask each of you to please figure out what you would do when it comes your turn to play. Again, the demon's got tons of money. It doesn't care what you choose. It only cares that it predicts correctly what you're going to choose. And again, if it predicts you'll choose box B, it puts $1 million in there. If you do that, you'll get $1 million. If it predicts you're going to choose both boxes, it puts nothing in box B. You'll still get the 1,000 at least, right? The only downside is if you choose box B only and the demon once in a blue moon has predicted in your case incorrectly, then you'll get nothing. And of course, if you choose both boxes and once in a blue moon the demon incorrectly predicts you'll choose box B only, it puts the $1 million there, and then you luck out and you get the maximum, which is the $1 million and the 1,000, but that's very unlikely, right? Probabilistically, these outcomes happen almost with no frequency, right? These outcomes happen with the greatest frequency. So if you play the odds, obviously you would choose box B only. But if your dominant reasoning prevails, then you're going to get something. You'll never run the risk of getting nothing. You're always going to get at least 1,000. Okay? And you might hit the big time and get both. So, if everyone's clear about this, are there any questions? I'm asking you one last time if you're clear about how to play the game. If you just tell me if you are, please. All right, Rachel asks, does the demon know you from your whole life? No, the demon doesn't know you from Adam or Eve. The demon just has this uncanny ability when you step up to the table, and you see box A, and there's 1,000 in there, and you see box B is gift wrap. You don't know what's in there till the demon puts something in there or doesn't. You can't see behind the box. The demon is just really able to read your mind at that moment, okay? The demon cannot read everything about you. The demon is only, it has this kind of one power, and that one power is it's able to predict very accurately whether you're going to choose box B only or whether you're going to choose both boxes. That's all it knows. It doesn't know you well, it doesn't know you personally, it doesn't know your instincts. It just at the moment that you're making up your mind, it somehow has this ability to predict what you're going to choose. Okay? Fair enough? It's an imaginary scenario, right? There's no such demon. We're not asserting that there is. But we're just saying this is the one skill the demon has. And again, you've been able to watch a lot of people play, and you notice the demon's almost never wrong. Almost never. Most of the time, the demon correctly predicts what the player will do. And how do you know if the demon's predicted correctly? Because you know that the demon is predicted correctly in the case of all the other players, because every time, almost every time a player chooses box B only, there's $1 million in it. That's how you know the demon, has correctly predicted that choice, because it puts the million in there if it thinks it will you choose. And also, almost every time the player chooses both boxes, there's nothing in box B. The player gets the 1,000, but doesn't get the million because there's nothing in box. Because the demon, you can see from watching the other players play, right? It's transparent. The demon's prediction is not transparent, but the result of the demon's prediction is transparent. Because every time the player actually makes the decision, then you're going to know what's in box B, aren't you? You're going to find out. You're able to watch. Okay, is that clear to everybody then? Are any other questions? If there are no other questions, then I'm going to assume you all understand the game, and then you're going to, when your turn comes, you're informed about the two possibilities, so you're going to make your decision. Okay, so here's what I want you to do. I want to see, first of all, how many. I'm going to stop the share. Well, I'll keep the share so you can see the choices, right? But I'm going to open the chat room here. It's still open, and what I'd like you all to do is I guess I could take a poll, but I'm not sure I know how to do that, so we'll keep it really simple. How do I take a poll? Poll 1. Oh, I could take a poll. Okay, I'm going to add a question. I haven't done this before, okay, so bear with me. And how does this work? Type your question here. Okay. Enter a title for this poll. Newcomb's problem. We'll try this, okay? I'm going to try this. So, you could be anonymous. I'm not even going to ask your identity. And, okay, so do you choose, that's the question. Do you choose box B only or both boxes? Okay? So that's the choice. And I'm saving this. I don't know where it shows up. If I've done this correctly, somehow or other, you should have the option of answering now. Is anybody seeing the poll? Nope, you're not seeing the poll? You don't see the poll yet. Okay, let me try again. Poll 1. Maybe I had to be out of the screen share. Okay? Now I'm going to ask you again, and I don't really understand what to do after I save it, but it's a single choice. And type your question here. Do you, poll's name is Newcomb's problem. So while I'm doing this, you think about your choice. Do you choose box B only or both boxes? Now, there's only two answers, right? Possible answers, box B only or both boxes. Answer 1 or answer 2. I'm seeing something going on. I guess I have to save it or cancel it. Those are my options. So I'm saving it. And apparently it's there. So it's saved, but I don't see anybody's answers coming in yet. So it's unclear to me whether anybody's seeing the poll or not. Can anybody speak and tell me if you're seeing anything?
Yeah, we're
Yeah,
not
we're not
seeing
seeing
it yet.
anything.
You're not seeing anything. Okay, well, I mean, I don't know how to use polls, okay? I think that proves it. I've done whatever I can do on the screen. I've put what I filled in the fields, and I've saved it. So maybe I have now to find it somewhere. I've not add. Oh, I have to add the poll. No. Add a poll, save a poll. Look, it's not very clear to me how that works. So never mind. Okay. It's not at all clear to me. I don't know how to launch the poll because I don't see a launch button. It's again, everything is in the hands of web developers who know how to do everything except at times communicate clearly to the users. So this was a fail, and I apologize. I thought it would be easy. My bad. But let's do a different thing. I'm going to ask you to enter into the chat room if you don't mind. Just type in whether box B only or both boxes. Those are your choices, right? Okay, box B or both. Box B or both boxes. Just go ahead. Please, just everybody once, okay? No, I already know Alexandra is not an answer. I need to know box B only or both boxes. Okay, please type. You've already entered. Thank you. Okay, cool. I'm seeing some responses. Okay, let's keep going. Keep going. Keep going. Try not to be influenced by the others. Okay, I see everybody's answering, and I wish I could have done the poll, but in any case, this is working. I'm getting to see people's answers. There are 30 of you in the chat room, so 30 of you should be able to respond. And most of you, at the moment, are responding. Some of you are not responding whatsoever. But those of you who are responding are almost all, in fact, all responding box B only, which is very interesting. And I'll tell you why in a moment. All right, I'll tell you why it's interesting. More than half of you now have responded. Thank you for your responses. Okay. So first of all, here's what Robert Nozick found, and he did this for many years in Harvard with his classes. When he taught this problem, he usually taught it also in his intro class there, and he wrote about it in the actual chapter where he introduced the problem. He recorded some of his experiences with his students, and I've been doing this for years at City College also. And what Nozick said, and what I've experienced, except for this morning, which is an exception, is that the class usually divides pretty much half and half. Normally. I mean, we're not at all in a normal situation. But normally in a live classroom with live students and a secret ballot, normally I do that with secret ballot. I ask people to write it and hand in a slip of paper. So normally it's about a 50-50 split between people choosing box B only and choosing both boxes. Normally it's about 50-50. And Nozick adds that in his experience, the people who choose whatever choice you make, people who choose box B only think that people who chose both boxes are being silly or foolish, and people who choose both boxes think that people who choose one box only are being silly or foolish, and they have good reasons either way for making their decision. So anyway, those of you who have made your decision, you now have a kind of a term. The class is logical instead of greedy. Well, that's a very interesting observation, Alexandra. I think you put your finger on something important. Just let me tell you that in the terminology of the game, you're either a one boxer or a two boxer. Okay, so those of you who chose box B only, and it looks like it's unanimous among those who responded. I didn't explain that box B is better off, Rachel, and maybe I prejudiced the case, okay? It may be my fault in the way I presented it. I just wanted it to be clear. I didn't say that box B is better off at all. As a matter of fact, I said the opposite. If you reason according to dominance, then choosing both boxes is better off. Because if you choose both boxes, you're better off no matter what the demon predicted. Because 1,000,000 plus 1,000 is better than 1,000,000, and 1,000 is better than nothing. So maybe I've misled you with my explanation. I know some of you are okay with it, but I have my suspicions right now that you've misunderstood me, and therefore you've been swayed by what I said rather than by the actual calculations. And the dominance principle normally persuades half the people to choose both boxes, because if you choose box B only and the demon's wrong, you get nothing. But if you choose both boxes, you're guaranteed at least $1,000. And most of us would be pretty happy to be guaranteed at least $1,000, don't you think? I mean, if somebody guaranteed you $1,000, wouldn't you take it? Rachel says yes. So then why did you choose one box and risk getting nothing? Remember, if you choose one box and the demon predicts that you're going to choose both, and the demon doesn't put anything in box B, and you only get the 1,000 that's in box A, but at least you get the 1,000, right? So it may be, I've never taught this online, and I have a very strong suspicion now that presenting this thing online has somehow resulted in skewing the way it's being communicated. So okay. That's also true, Samantha, and it's nice to hear you pipe up. And I think that your argument about percentages is a very good one. It's a very sound observation that 99% are fantastic odds, and you put your trust in things with worse odds every day. That's exactly right. We do, and sometimes we have to. That's a very good point. So you're now being given really, really good odds on winning $1 million, and you're willing to take your chances and say, okay, if I don't get the 1,000, I'll give up the 1,000, but I have a really good chance of getting $1 million. So that would be your reason. Am I right? That's your reason for choosing box B alone. Is that correct, Samantha? Yeah. And that's what most people, I think, would say. Do those of you who chose box B have similar reasoning to Samantha's? Is that more or less how you were persuaded? Please tell me. Is that more or less what persuaded you to choose box B only? Because everybody did. Is it because the odds of winning $1 million are so high? Yes, Randy, also you're persuaded by the odds? You are? Anybody else? Was that the reason why? I mean, everybody chose box B. It's never happened. So you must have had a good reason. Aside from my, I'm trying to narrate this in an even-handed way. Maybe I skewed my own presentation. Normally there's a few people who say, hey, I'll take the 1,000 no matter what, because the 1,000 is better than nothing. Okay, but none of you did that. So is it the case then that most of you were swayed by the odds? That you believe that the demon is going to correctly predict what you do? Yes? No? Maybe? Yes? Okay. Maisha, yes, also. Same degree of belief in the demon's ability to correctly predict your choice, right? Yeah. Many of you, if not most of you who responded, were probably thinking along those lines. So you're one boxers. You can try this at home. It's a lot of fun. Yeah, you take the chance for worse odds, Ruby, and that's also a good point. And remember, if you want to go into the fine print, if you go into the more nuanced computation, it's not difficult. You could just experimentally, if you understand how to calculate your expected utilities in both cases, and you have the payoffs in front of you, you can choose arbitrarily to play with a different probabilities of successful prediction. And you'll discover that as long as the demon is right more than half the time, you're still going to get the result that maximizing expected utilities will prescribe that you choose box B only. The demon doesn't even have to be that good. As long as the demon predicts correctly with greater than random frequency, you're still better off choosing both boxes. So, I mean, that's the same reasoning. 1,000 compared to a million is so little, you definitely, when you have a good chance of winning a million, you're going to go for the million. And that's a fair argument, Ruby. I mean, I think a lot of you were probably thinking that way. That's not different really from Samantha's argument either. You're looking at the probabilities and you're saying, hey, I have a really good chance of winning a million, I'm going for it. Now, if the demon's predictions get lower, Randy, that's exactly right. If the demon were having a bad day and you're watching the demon and the demon is nowhere close to 100%, the demon's predictions are sinking to a success rate of just, like 55%, what will happen in the calculus is that the expected utility of choosing box B alone will fall. Obviously, as the demon's successful prediction rate falls, that payoff will fall in the calculus, and the payoff of choosing both boxes will rise, and at some point they're going to be even, and that's where basically you might as well take both boxes, and that's at 50%. At 50%, it's no longer the case that you're better off with box B only. And obviously, if the demon's a very poor predictor, you're better off with both boxes, clearly. So you could try this at home as long as you can explain the problem. You could put two boxes on the table and pretend there's 1,000 in one and the other one nobody can see into it, so you could, they can understand at home how the problem works. Or show the slides. They're in the folder. You can help yourself to the slides I've just shown you. And if you chose one box only, which most of you did, then you're called a one boxer. Okay? If you chose two boxes, nobody did this morning. That's the first time it's ever happened. They say there's a first time for everything. I believe it. If you people who do, and there are many people who do choose two boxes though, and they're called two boxers, right? So you're a one boxer or a two boxer in this context. Most of you are one boxers. I'm mostly, if you're wondering, I'm usually a one boxer myself, given a very high success rate of prediction. I'm pretty much a one boxer, although I have a really good friend who's a philosopher, and we agree on almost everything philosophically. We're very close in our agreements, but not on this. He's a two boxer. And he thinks I'm being silly for being a one boxer, and I think he's being silly for being a two boxer. So there you have an illustration of the divergence. Even your best friend might disagree with you. You could try it with your best friend. You obviously maybe share a lot of tastes. If you have best friends that probably share many things in common, and so conduct that experiment. See if your best friend is a one boxer or a two boxer as well. It's not going to break up a friendship. It's just a game, but it'd be interesting to know. Yes, Randy, there's no question. As the demon's prediction rate drops, then there's a convergence, not a divergence. You see, dominance always tells you you're better off taking both boxes. But if the demon's prediction rate sinks to 50% or less, then maximizing expected utilities will also flip its prediction, because it's all driven by the probability, right, within this structure. So what happens is, in that case, if the demon's prediction rate gets below 50%, then there's no difference, because maximizing expected utilities will also tell you to go with both boxes. So there's no more dilemma in that case. The dilemma only arises, if you like, because the demon has an uncannily high prediction rate. Okay? Successful prediction rate. So that's basically how it works. That's the same as the calculus of the two-person prisoner's dilemma. You know, if you believe that your opposite number in the two-person PD is going to cooperate with a very high probability, then maximizing your expected utility tells you that you're better off cooperating. You get the Pareto optimal outcome that way, right? So it's a parallel reasoning. But there's something else now we could look at. And so let me ask you the same question with a different set of payoffs, okay? So now let's go a different route. Let's suppose that instead of $1 million in box B or nothing, right? You know, we're going to have the same problem, same game, same demon, same odds. But now I'm going to pose the question differently. I'm going to change the amounts in the boxes. I'm going to ask you all to, once again, to make a choice between box B only or both boxes. Now I'm going to say that for the sake of argument, that the two amounts are not 1,000,000 and 1,000, but rather the two amounts are in box A. There's 1 million there. Okay, box A has 1 million sitting there, and that means if you take both boxes, you're now guaranteed $1 million. No questions asked, right? Because the million's sitting there in box A. Box B now is either going to contain $1 billion or nothing. Again, depending on the demon's correct prediction. If the demon predicts you're going to choose box B only, it puts 1,000 millions in there. That's $1 billion it puts into box B. If the demon predicts you're going to choose both boxes, in other words, get the million that's in box A, it's going to put nothing in box B. Okay? So the actual mathematics are the same, and the ratio of what's in the boxes is the same, because 1 million in the first instance is 1,000 times more than what's in box A, and in this case, 1 billion is 1,000 times more than the million that we're now starting off with in box A. So is everybody clear? We're playing another time, and now the demon has already put 1 million in box A. So if you choose both boxes, you got $1 million. You're guaranteed that $1 million. If the demon predicts you choose box B only, it puts $1 billion into box B. So you have a chance to win $1 billion. You have a chance to win $1 million for sure, or you have a chance to win $1 billion plus $1 million, right? It's the same structure. Does everybody understand that? I only have changed the absolute amount of the payoffs, not the ratio, right? The ratio is still 1,000 times more possibly in box B than in box A. You don't know. But now there's $1 million in box A for sure, and the demons are either going to place $1 billion in box B or nothing in box B. Now it's your turn to play the game. Are you going to choose both boxes, or are you going to choose box B only? Please, if you don't mind, put it into the chat room. If you choose both boxes, you got $1 million. If you choose box B, you got $1 billion or nothing. Same high success rate, but you're guaranteed $1 million for choosing both boxes. Okay? Box B still. Samantha, Ruby, still box B, both. Okay, Rachel's changed her mind. Okay, and you're still going. You're still going for the $1 billion. Okay, and Tia Gay is taking both this time, and Javier is taking both this time. Okay, so you see what we've done is we haven't changed the structure of the problem, but we've changed the absolute amount of money that's in the boxes, right? So I was able to convince some of you now to switch your prediction by guaranteeing you $1 million. I might switch too at that point, yes? And Remo also is going for box B. Okay, now am I right? Are you down? Those of you who changed your minds, is it because now you're guaranteed something really worthwhile, like 1,000, you could take it or leave it? That's not going to change your life that much. 1,000 is a lot of money, but it's not going to be life-changing, whereas $1 million will be life-changing. Am I right? Is that why those of you who changed your minds? Please share your reasons. I'm interested in those who change. Those who didn't change, I know you still believe in the demon, and you might just get $1 billion out of it. Now you might be playing in a really big arena, okay? But those of you who changed, it's because $1 million is really life-changing, and you're guaranteed $1 million, right? So why would you take a chance? Is that correct? Yes, Javier? Yeah, this is why. Now you're going for both boxes, yeah? So Rachel says, my knee-jerk reaction is both, so I know I won't trick this demon thing. Well, I'm not sure what that means. But basically, if the $1 million is sitting there, then it makes obviously a huge difference, because it's so much more to be guaranteed than 1,000 that, you know, you'd rather take the $1 million and run, okay? $1 billion is too much money in my head. Yeah, I can't process $1 billion either, so I would take the $1 million myself. I'd become a two-boxer if there were $1 million in box A. If there's 1,000 in box A, I'm not going to be a two-boxer. For that, I'd rather take a chance on winning the $1 million. But I agree with you, Randy, that $1 billion is too much. Most of us, you have to be a billionaire to be able to process 1,000 millions, right? I mean, Bill Gates can process it. Oprah can process it. You know, Jeff Bezos and these billionaires, multi-billionaires, they can process it. But the rest of us can't. So let me ask you now the flip side of this. I'll do it again. Same thing. Now suppose that we keep the same problem, but we put only, let's say, $1 in box A and $1,000 in box B, right? Same demon, same success rate. Now, if you choose both boxes, you're guaranteed $1, right? Or if you choose box B only, you might win $1,000. I'm sure that most of you are going to say, hey, $1 is not going to change my life, but 1,000 would make a difference, so therefore I would go for box B. Is that correct? If we change the payoffs again, we keep the same ratio. Notice in every case, the ratio is 1,000 to 1, right? What's in box A compared to what might be in box B is always 1 to 1,000, but the absolute differences are such that they're going to change people's minds, right? Do you get this? Yes, yes. It's not because the house never loses, Denise. It's because the $1 that you're guaranteed is probably not that significant compared to the 1,000 that you might win, correct? I mean, the house doesn't care. The house is the demon. The demon just wants to correctly predict your choices, yeah? So you want to think about this, the sub-message, what lies underneath the difference, why the same principles apply, but when you start changing the payoffs in a game, and this is true of every game in economic terms, when you start changing the payoffs, even though the ratios are the same in the problem, the absolute values of the payoffs will be important depending on our own life situations. What seems like a lot of money to one person may seem like only a little money to somebody else. And that's why you don't get the same, even though everybody may be deemed to be rational, they don't make the same choices because the amount of money that is there is a fixed sum, but it has differing values to different people said a different way. In other words, if someone's asking for money on the street, someone is panhandling, and you may give them $1, that dollar might mean an awful lot to someone who's trying to buy a muffin or a cup of coffee or a lunch or whatever. $1 might make a big difference to them. It might not make a big difference to you, and would make no difference at all to Jeff Bezos, right? Whereas if somebody on the street asks for $100, you're probably not going to give them $100 because that makes a much bigger difference. Me too. And whereas somebody like Jeff Bezos could easily afford it, it would make no difference to him. So when people are asking for money, the amount that they're asking for is also going to seem large or small depending on the means of the person who is giving. Yeah? And so when you stand to win money in a game, it's the same thing. The absolute value of the prize may be the same for all the contestants, but the value of that absolute amount of money may differ from contestant to contestant depending on their particular relative means, okay? So that's the tricky thing about money. It doesn't conserve its value for each person in a game, even though the same amount of money may still be there. It may have differing values for differing people. Is that clear? Is that all clear to you? Yeah? Good. Okay. So if you start changing the amount of payoffs, then you can also influence people's. If you're playing this game with a billionaires, imagine we're playing the game in a room full of billionaires, right? And we're saying to them, there's $1,000 in box A. They're not going to care. And there might be $1 million in box B. I don't even think they'd care very much, but most of them would go for box B only because they don't care about $1,000. Yeah. If you put $1 million in box A and they could go for $1 billion, if they were a bunch of billionaires, they'd probably still want to go mostly for box B only because $1 million might not make a difference to very many of them either if they have that much money, right? So no matter who's playing, the moral of the story is that the actual value of the money will differ from player to player, even though it's a fixed amount of money, all right? I mean, you already knew this. But you see how changing the values, not the ratio of the payoffs, but changing the actual absolute value of the money in the boxes could indeed sway people into making different choices, all right? Which is a factor we're not really focused on. It will change the nature of the decision-making process without in the least altering the actual principles of choice, which are still going to diverge, given a high enough success rate. All right, that wraps up Newcomb's problem. I hope you enjoyed playing the game this morning, and I hope it gave you some food for thought. Are there any other questions before I sign off for today? Anybody want to have the last word? Any questions or observations? Okay. Well, with that, I want to congratulate you for completing the course as prescribed. Of course, you haven't yet handed in your final work for me or for your other instructors, I assume. But we have completed officially the course of lectures on the syllabus, so good for you. And I will look forward to seeing my group on Thursday. We'll look at a couple of spin-offs of this problem. It actually, believe it or not, has real-world applications, believe it or not with money, but with other things. And also next Monday, I remind you, is our last official class, and I will be happy to have a review. You bring your questions. I will not introduce new material. I will solicit questions from you on anything we've covered in the third section, or more broadly, any philosophical question you may wish to raise. Will be fair game, and that will be our last class, Monday the 17th. If nobody shows up, I have plenty of work to do. If people show up and want to take advantage of me as a resource person, then by all means you're welcome, and I'll do my best to give you some insights or information or guidance on any philosophical question you may wish to raise. Okay, other than that, I wish you a very good day and a very good week, and I'll look forward to seeing you all, some of you Thursday, and hopefully all of you to wrap things up next Monday, okay? You're more than welcome, Remo. You're more than welcome, Rachel. You're more than welcome, everybody. Have a great day, and play the Newcomb's problem with your best friend, and see if they're one boxers or two boxers, okay? Bye for now.